Hello, Integrated Math 1. Welcome to lesson R.7-1A. We're going to be graphing systems of equations. We're going to be talking about systems of equations. You're going to find out what a system of equation is, how to solve it throughout this unit. We are, of course, piloting Reveal, so that's why we've got our little R in front. If you have the book, where we will eventually start on page 387, but for now, we just have a little warm-up that actually is not in your book. So go ahead. I would like you to try this out. I would like you to determine, and you may need a little help, it's cool, but try it out. Determine whether each ordered pair is a solution of y equals 3x, a solution of y equals 2x minus 2, a solution of both equations, or maybe a solution of neither one. So is each ordered pair, is this ordered pair a solution for this guy, and both of them, neither of them? And same thing for the next one. And just a little hint, if you want a little hint to get you started, just a little hint that that's x and that's y, right? Seems like you could, plug them in and see if they work. Go ahead and hit pause, work these out, hit play when you're ready to check your work. So I'm going to go ahead and I'm going to start with the first one. So I have y equals 3x. And I'm just going to plug in for y. Instead of y, I'm going to plug in a 2. Instead of x, I'm going to plug in a 2. And 3 times 2 is 6. Which is not equal. Okay, well, it's not a solution of the first one then. I guess we've established that. And, but there's a second equation. We're supposed to check that one as well. So y equals 2x minus 2. Fine. Everywhere I see a y, I'll plug in a 2. Everywhere I see an x, I will also plug in a 2. And, of course, 2 times 2 is 4. And 4 minus 2 is 2. Hey, that one worked. So that one didn't work. That one did work. So that means it's a solution of y equals 2x minus 2. So it is a solution for that equation, not a solution for the other equation. Whoa, okay. Let's try out the other one. Again, this is my x, and if this is my y, well, let's plug in. So for our y equals 3x, instead of a y, I'll plug in -6, and instead of an x, I'll plug in a -2. And then I do want to clean up just a little bit. The lights, they're always doing funny things on me in here, aren't they? So I still have a -6 over here, and then, of course, 3 times a -2 is -6. Yay, it worked. So I know that y equals 3x is a solution. That is a solution for y equals 3x. Yay. Let's try the other one. Y equals 2x minus 2. So instead of a y, I will plug in a -6. And instead of x, we'll plug in -2. And this one I have to do a little more work on. 2 times a -2 is -4. And -4 minus 2 is a -6. It works for this one as well. Oh my gosh. So it turns out this is a solution of both equations. Ooh. Now that's interesting. So this point was on that line, but it wasn't on this line, right? Whereas for the second one we did, this point -2, -6, it's a solution for both. That means this point is not only on the first line, it's also on the second line. That point is on both of those lines, which is interesting. That comes us to this whole idea of systems of equations, that if you have two equations where they intersect, right, where they meet up, that's going to be where the solution is for both of them. That'll be what's true for both. So, yeah, we are graphing systems of equations today. We're taking this in stride, so we're just doing day 1 today. We'll hit day 2, next time. But before we do, there is some vocabulary. So I keep using the word system of equations. I keep using that phrase. Maybe we should, define it. So when we're talking about a system of equations, it's just a set of 2 or more equations with the same variables. So like we had x's, we had y's. They had the same variables. Awesome. And so it's a system of equations. When we're talking about a consistent system of equations, a system of equations with at least one ordered pair that satisfies both equations, that's a consistent equation. Hey, there's at least one point on that graph that's true for both of those equations. Yay. It's on both of those lines. Now, there are a couple scenarios that can happen. So with inconsistent, I want to point out that with inconsistent, there's two things that can happen. If a consistent system has exactly one solution, it is said to be independent. So like if I were to graph the lines, and I'm just going to use a couple colors here. So if I'm like x-axis and y-axis, except I said those backwards, and I'm like, here's a line, woo, and then I was all like, here's another line, woo. That point, you see how they intersect in exactly one point? I would say that not only is it consistent because it does have a solution, it has a place where they meet, I would also say it's independent. There's only one solution, that's it. There's one solution, that's it. It doesn't depend on anything else. However, if a consistent system of equations has an infinite number of solutions, we say that it is dependent. Yeah, so we get a different situation going on there. So let me draw and kind of show you what I'm thinking here. So if I have two equations and I graph them and I'm like, hey, they intersect, but if I graph one of them and it looks like that, but then I graph the other one and I'm like, whoa, it's right on top of it. I'm like, holy crud, they're the same line. If I go to graph my system of equations and I realize that they're the same line, that means there's an infinite number of solutions. It means every solution for the one line is also going to be a solution for the other line because they're, well, the same line. We say that it is dependent, right? So if a consistent system means it's got at least one solution. Can have one solution or infinite solutions, but it's got at least one solution. If it only has one solution, like this guy, it's independent. If it has an infinite number of solutions, like this guy over here, we say it's dependent. Now, you know it's possible to not have any solutions at all. So a system of, I can say this. A system of equations with no ordered pair that satisfies both equations, you're like, there's no solution here. We say it's inconsistent. And to give you an idea of what I'm thinking, here. Choose my x-axis and my y-axis. There, I keep drawing y first and say x first. So let's say I graph a line and I'm like, ooh, so beautiful. There's my line, yay. And then I have another line and I'm like, ooh, so beautiful. Oh, crud, they're parallel. If this happens, if you have parallel lines, there's no solution. Solution to a system of equations is where they intersect, right? It's where they meet up. If my lines are parallel, they don't meet up. There's no solution because it has to be something that works for both of them. There's nothing that works for both of them. Boom. So we say that that is an inconsistent system. So now that you have this in your head, you got this in your head, these guys are consistent, and this one is independent, and this one's dependent. And it's because they actually intersect. This one only intersects once, so I say it's consistent and independent. This one intersects forever, so I say it's consistent and dependent. And then, of course, if I have a system that never intersects, ever, there's no solution there, we say that it is inconsistent. Let's get in your head a little bit. You got this? Did you make some notes on this? I hope you did, because now I've got an example for you. I would like you to try out, dun, 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 example number 1. So I would like you to please use example number 1. That's why it's there. I would like you to use the graph to determine the number of solutions a system has. Remember, we said we have one solution, infinite solutions, no solution at all. So start off by determining how many solutions do we have. And then once you've decided that, state whether the systems of equations is consistent or inconsistent, and if it's independent or dependent. And it might not be some of those. That's okay. Hit pause, work your way through this, and then hit play when you're ready to check your work. All right, we said a solution is any point that hits both lines. It's true for both equations, right? Not just one, it's got to be true for both of them. So with that in mind, and actually we'll grab another color so we can see it a little better. I'm going to use purple. With that in mind, I can see that there is a single point where they intersect. Check that out. There's one spot where these two lines meet up. So there's one point, one ordered pair that works for both lines. So I'm going to point out that there is one solution. All right, so going back to our vocab from earlier, if there's one solution, does that make it consistent or inconsistent? Well, if it has a solution, it's consistent, right? I mean, the very fact that it has a solution at all makes it consistent. Awesome. And because it's consistent, I now have to decide if it's independent or dependent. Again, if we go back to our vocab, our notes that we made on our vocab earlier, it says it intersects at exactly one point, so that means it's independent, right? So I'll make that a note of that. Independent. Sweet. Look at us. Although, if you want my fancy explanation, there it is. Since the graphs of these two lines intersect at one point, there's exactly one solution. So the system is consistent and independent. Awesome. Good job, us. Do it again. Example 2. Do it again. Use the graph, determine the number of solutions a system has, then state whether the system of equations is consistent or inconsistent, and if it is independent or dependent, hit pause, write it out, hit play when you're ready to check your work. All right, first of all, I'm looking at these lines and they don't intersect. And in fact, there's a reason they don't intersect. Check out the slopes. Oh my gosh, they have the same slope. Guys, these lines are parallel. Oh my goodness. Because these lines are parallel, there is no solution. We said in order to be a solution for the system, it has to be a point that works for both lines. The lines have to intersect somewhere. These will never intersect. So there is no solution. Let's take this a step further though. So since there's no solution, according to our vocab and our definitions we wrote down earlier, that means this is an inconsistent system. And so I don't even have to consider independent or dependent because independent and dependent, those only apply in consistent situations. And this is not consistent. They will never intersect. It's kind of sad when you think about it. You know, we've been doing this with graphs, but did you notice they gave us the equations as well to kind of help us out? Can we do this again, only without the graph? What if I give you just the two equations of the system and no graph this time? No Desmos, no graph, just looking at the equations. Can you logic your way through this and determine the number of solutions the system has, whether the system of equations is consistent or inconsistent, if it's independent or dependent? Go ahead and hit pause to think your way through this, and then hit play when you're ready to check your work. Okay, so I was looking at this problem and I had a few thoughts. I'm going to use a couple different colors here. I first started looking at the slopes, right? This is the whole y equals mx plus b. You got to love that slope-intercept form. It tells me all the things. So I can see that my slopes are the same. So I'm making a note of that. Slopes, same slopes. I'll write it that way because then I can use fewer words. But I'm also looking at the y-intercepts, and I'm noticing that I have different y-intercepts. Okay. So I have the same slope, but I have different y-intercepts and a really crazy t. So this tells me something, right? If they have the same slope but different y-intercepts, guys, these lines are parallel. If my lines are parallel, they're never going to intersect. If my lines are parallel, they never intersect. So that means there is no solution. So we answer the first part. And we already talked about this. If there's no solution, if they never intersect, then it's going to be an inconsistent system. Fine, be that way. And since it's inconsistent, it's not going to be, we don't consider it independent or dependent. It's just inconsistent. Yikes. All right, that was pretty easy. That was pretty easy, right? I mean, you could look at that and you could be like, there's my slope, there's my y-intercept. I'm going to mess with you, though. Are you ready? I'm going to mess with you. Are you ready? It's part of the joy of teaching. Let's do this again, only with these equations. Hit pause. Give this some thought on how you could sort through this, and then hit play when you're ready to check your work. You ready? You ready? I'm ready. So I looked at these and I was like, slope, y-intercept. So you know what I thought? I thought, you know what? The first thing we should probably do is let's write both these equations in slope-intercept form, right? I mean, that'd make things easier. So I'm going to take these equations. Remember, that's code for solve for y, right? Solve for y. Get the y alone. So I'm going to take this lovely 4y minus 6x equals 16. And I'm just going to get the y alone. I'm going to start off by adding 6x to both sides. Pew, pew. So now we have 4y equals, it's a positive 6x and a positive 16. So I'll say plus 16. Ooh, y is not alone just yet. So let's go ahead and divide everything by 4. And please remember, everybody gets divided by 4. It's just, we got to be fair, right? Come on now. So I have y equals 6/4. I want to leave it as a fraction. I don't really want to do a decimal, but I also don't like the 6/4. Can we simplify that? I think if we divide those each by 2, right, that becomes 3/2 x. And of course, 16 divided by 4 is 4. Yay, good job us. Let's now do the same thing for the other equation. And I'm going to just leave myself some space because we're going to make some notes in the middle. So I'm going to leave myself some space. Let's do the other equation. 9x minus 6y equals negative 24. And let's just get the y alone. I want to get rid of the 9x. Please note that's a positive 9x. So I subtracted 9x from both sides. Pew, pew. And I have negative 6y equals negative 9x, and that's a negative 24. Remember, with slope-intercept form, we like to have the x in front. It's just helping me find my slope. That's all I want. I don't like that the y is not alone. We should get the y alone. So let's divide by negative 6, but we have to do it to everybody, right? We got to be fair. Let's do it to everybody. So those cancel out. And I have y equals negative divided by negative is a positive. And again, I don't want to leave it as 9/6. I do want to simplify my fraction. So if I divide each of those by 3, 9 divided by 3 is 3, 6 divided by 3 is 2. Negative divided by negative is a positive. Awesome. Okay, so 3/2 x. Negative 24 minus 6. Negative 24 divided by a negative 6 is a positive 4. Wait. Oh my gosh, look at what happened this time. So this is a little different from what we've encountered before. I mean, we have the same slope. We have the same y-intercept. Are you catching that? Oh, guys, we mentioned it a little bit at the start of the lesson, but this is the first time we've seen it. This is the same line. All right, if it's the same line, these lines are literally, if we were to graph them, they would literally be like right on top of each other. So that means that there are infinite solutions, right? Those lines would be like smack dab on top of each other. So we have an infinite solution situation, which means that it is consistent because they do intersect. So that makes it consistent. But now that also means if it's a consistent system, we have to decide if it's independent or dependent. Well, looking at my definitions, I still have my notes sitting right here in front of me. looking at my definitions, we said if a system of equations has an infinite number of solutions, which we just decided it did, it is dependent. So dependent it shall be. Woo! Awesome, guys. Well, as always, I hope you found this helpful. I hope you found this useful. If you've got questions or concerns, come talk to me. I'm around, and I'll see you guys soon. Bye.